Okay, so welcome back, everyone. The online analysis seminar broadcast from St Andrews. So today's speaker is Amlan Banaji, and he's going to talk about intermediate dimensions of Bedford-McMullen carpets. So over to you, Amlan.
Okay, thanks very much, John. So this talk is going to be based on joint work that I've been doing with Istvan Kolossvary. And I'm also grateful to Istvan for making many of the pictures that you'll see in these slides. So I won't dwell too much on the general fractal geometry background, other than just to say that we've got the Hausdorff and box dimensions to fractal dimensions, and the Hausdorff dimension of sets will often be less than the box dimension. And when this happens, this generally indicates that the set has an inhomogeneity in space. A common way of generating fractals is through an iterated function system, which, if we recall, is just a finite set of contractions on some closed subset of Euclidean space. And by Hutchinson, there's a unique non-empty compact attractor that's equal to the union of its images under the different maps. So in particular, if each of these maps is a similarity, which means that it contracts lengths by a fixed amount, then the set is self-similar and it will have equal Hausdorff and box dimensions. But in this talk, I'll be interested in self-affine sets. So I'll be interested in the case where each of these maps S sub I is affine. So it will be a composition of a linear map with a translation. And for planar self-affine sets, if we assume a separation condition, then they will typically have equal Hausdorff and box dimensions. So this is by an important recent result of Barani, Hochman, and Rappaport. But it is possible for the cylinder sets, as we'll see, to line up in a particular way that means that the irreducibility condition that they assume fails. And when this happens, the set can have distinct Hausdorff and box dimensions. And this is exactly what happens in the case of Bedford-McMullen carpets, which are going to be the fractals that this talk will be about. So these are a widely studied class of self-affine fractals in the plane, and they were introduced independently in 1984 by Bedford in his PhD thesis and McMullen. This is the Fields medalist McMullen. And the construction is as follows. So we take a square and we divide it into an m by n grid where m is some integer greater than or equals 2 and n is greater than m. So in this case of this carpet that we see down here, m is 2 and n equals 3. And what we do is we just take some subset of the rectangles from this grid, and the iterated function system will be composed of those affine maps that send the square to each of those different rectangles. So more explicitly, this will be multiplication by this matrix, 1 over m, 0, 0, 1 over n, and then addition by whichever translation vector takes you into the required rectangle. Let's also set up some notation. So this constant gamma is going to be very important. So that's just going to be log n over log m. So in this case, it will be log 3 over log 2. Capital M is going to denote the number of non-empty columns. So in this case, that is 2. And n sub I hat will denote the number of maps in the column I hat. So for example, in this case, n sub 1 will be 2 because we've got 2 maps here, and n sub 2 will be 1 because we've got 1 map here. And capital N is going to denote the sum of the different ni, so the total number of maps. So in this case, capital N will be 3. And this is the simplest example of a kind of a non-trivial Bedford-McMullen carpet, really. So then the fractal is generated by basically iterating these cylinder sets. So here we've got the 3 first level cylinder sets. We iterate once more to get these 9 second level cylinder sets, then these 27 third level cylinders, 81 fourth level cylinders, etc. And then this procedure converges to the actual fractal, which is shown here roughly. Here are 3 more pictures showing 3 other Bedford-McMullen carpets on this same 2 by 3 grid. And you can see they form nice, pretty pictures. And what can happen is, as we saw previously, the cylinders can become more and more elongated as we iterate, and they line up with each other. And this can cause inhomogeneity in space. So if you see here, the cylinders are quite long and thin, and they line up with each other. And this can cause the Hausdorff and Box dimensions of the fractal to differ. So in 1984, Bedford and McMullen independently proved that the Hausdorff and Box dimensions of these carpets can be described by these simple formulae depending only on the parameters of the carpet. And in particular, the carpet will have equal Hausdorff and Box dimensions if and only if lambda has uniform vertical fibres, which means that lambda has to have the same number of maps in each column for the Hausdorff and Box dimensions to be equal. So throughout this talk, even if I don't always say it, I will always be assuming that the carpet has non-uniform vertical fibres and that the Hausdorff and Box dimensions are different, because that's the case that I'm really interested in. So if we look, for example, at these ones, the carpet on the left has 3 maps in this one and 1 map here. So this has got non-uniform fibres. Same with the middle one, 2 and 3, so non-uniform vertical fibres. But this one on the right-hand side has uniform vertical fibres. So the Hausdorff and Box dimensions will be equal. So I'll be interested in carpets like the left one and the middle one here. So I've talked a lot about Hausdorff and Box dimensions. What are they? Well, here are some equivalent definitions that are slightly different from the usual ones. The Box dimension can be described by covering your set in such a way that all the elements of the cover have got to have the same size. That's this condition that's written in red here. Whereas the Hausdorff dimension can be defined by covering the set, but without imposing any condition that the covering sets have got to have the same size. So for the Hausdorff dimension, some sets in the cover can be much larger than others. And it's this freedom that can sometimes result in the Hausdorff dimension being less than the Box dimension. So Faulkner, Fraser, and Kempton in 2020 noted that these may be regarded as 2 different cases, extreme cases of the same definition. And accordingly, they defined the intermediate dimensions in this way. So here we're covering the set with elements of the cover, and we have this important condition written in red here, which says that the diameter of each element of the cover has got to lie between delta to the power of 1 over theta and delta, where delta is just some small number and theta is a fixed parameter between 0 and 1. So in particular, when theta equals 1, we recover the Box dimension, and when theta equals 0, we get the Hausdorff dimension. Some basic facts about the intermediate dimensions. They do indeed lie between the Hausdorff and Box dimensions for all sets, and the function that sends theta to the intermediate dimension of some fixed set at theta is increasing, and it will be continuous when theta is strictly greater than 0, but not necessarily when theta equals 0. And I introduced another family of dimensions called the phi intermediate dimensions to explore that discontinuity further. And the intermediate dimensions are an example of a broader idea of dimension interpolation, where you construct a family of dimensions to interpolate between 2 other common notions of dimension. And the other main example of this is the Assad spectrum, which was introduced by Fraser and Yu in 2018. So what is known about the intermediate dimensions of Bedford-McMullen carpets? The main result of this talk, which I'll state a bit later, is that we've worked out exactly what the intermediate dimensions of all Bedford-McMullen carpets actually are. But before I state the main result, I'll talk about what previous work has been done to give partial progress to say something about the intermediate dimensions of these carpets. So lambda is going to denote a Bedford-McMullen carpet with non-uniform vertical fibres, as always. And Faulkner, Fraser, and Kempton showed that for small enough theta, there is this upper bound here for the intermediate dimensions of the carpet at theta. The upper bound is the Hausdorff dimension plus some constant, depending only on the carpet, divided by minus log theta. And this in particular shows that the intermediate dimensions are continuous at theta equals 0. So for sets in general, the intermediate dimensions might not be continuous, but for this class of sets, Bedford-McMullen carpets, the intermediate dimensions are continuous. I think the authors of this bound thought that this wasn't a very good bound that accurately captured the behavior at theta equals 0, but it's actually not so bad. The true behavior at theta equals 0, this is something that will follow from our main results that I'll state a bit later. The true behavior near theta equals 0 is that the intermediate dimensions behave like the Hausdorff dimension plus a constant divided by log of theta squared. Okay, so you've got these two constants, C1 and C2, such that the intermediate dimensions are sandwiched between Hausdorff dimension plus C1 divided by log of theta squared, and the same expression with the other constant C2. And in particular, this shows that the slope of the intermediate dimensions does tend to infinity as theta tends to 0, as this bound suggested. And I'll explain a bit later a little bit about how we can deduce this from our main result once we've stated our main result. The fact that the intermediate dimensions are continuous at theta equals 0, as proved by Falconer, Fraser, and Kempton, has some rather surprising and interesting consequences. By a result of Burrell, Falconer, and Fraser from 2020, this can be used to show that if we have a carpet whose Hausdorff dimension is less than 1 and whose box dimension is greater than or equal to 1, then for almost every projection pi from R2 onto a one-dimensional subspace, the upper box dimension of the image of the projection will be less than 1 strictly. And this is kind of interesting because not that much is known about the orthogonal projections of the box dimensions of orthogonal projections of Bedford-McMullen carpets, other than the fact that they've got to be almost surely constant by a general Marstrand type projection result. And another interesting consequence is that if B sub h denotes index h fractional Brownian motion on R2, which is some random function, then if h is greater than the Hausdorff dimension of the carpet divided by 2, then almost surely the upper box dimension of the image of the carpet under the fractional Brownian motion will be less than 2. So it's interesting that you've got this relationship between the Hausdorff dimension of the individual, of the actual carpet itself, and the upper box dimension of its image. And this was proved by Burrell using the fact that the intermediate dimensions are continuous at 0. Okay, so that was one bound for the intermediate dimensions that had been obtained before. What were some of the other previous results that had been obtained? Well, Falconer, Fraser, and Kempton proved a lower bound, which is this linear lower bound near theta equals 0 on this plot. This plot is for this, this simple carpet that we've already seen before. And that shows in particular that the intermediate dimensions are greater than the Hausdorff dimension strictly for all theta greater than 0 for Bedford-McMullen carpets. Istvan last year proved some upper and lower bounds, mostly focusing on large values of theta near theta equals 1, which show that the intermediate dimensions are strictly less than the box dimension for all theta less than 1, and that the graph is neither convex nor concave in general. So this bound up here is Istvan's upper bound, and this bound here is Istvan's lower bound. I also obtained a general lower bound for the intermediate dimensions that's got nothing to do with Bedford-McMullen carpets in particular, but in some cases that beat the other bounds for large theta. But that one is not shown on this particular graph because for this carpet, Istvan's lower bound is better than that. And also the bound that I mentioned previously of Falconer, Fraser, and Kempton is not shown on this graph because that bound exceeds the box dimension of the carpet for very, very, very small values of theta. So that probably wouldn't even show up on this graph very clearly if we tried to plot that on this graph. Now, one more thing to note is that the Hausdorff and box dimensions are usually very close together. So this figure is maybe slightly misleading. The Hausdorff dimension is maybe like 1.35 for this carpet, and then the box dimension is maybe 1.36 something. I can't remember exactly, but these are quite close together, and they've just been stretched out on the axis so that we can see more clearly what's going on in this small distance between the Hausdorff and box dimensions. Okay, so that's the previous work that's been done. So what does the actual graph of the intermediate dimensions of this particular carpet look like? Well, this is what it looks like. So I think this is quite nice. So what's going on here is that we've got this number 1 over gamma here, and the theta between 1 and 1 over gamma, we've got this nice smooth concave bump here. And then at 1 over gamma, if you look carefully, you'll see that there's a point of non-differentiability of the function, right? It goes through a phase transition. And then between 1 over gamma and 1 over gamma squared, we have another smooth concave bump, and then we get another phase transition at 1 over gamma squared. And then the same thing happens again and again. And then we see, as we've already mentioned before, that the slope tends to infinity as theta gets very close to 0. These features, we'll see a bit later on that these features can be proved for all different Bedford-McMullen carpets. It's not just particular to this one. So now what I'd like to do is to try to state our main result in terms of the formula that it satisfies the intermediate dimensions. And to do so, we need to define this function I of t as the Legendre transform of this function, log of 1 over m times this sum of n sub j hat to the power of lambda. So we take that function and we then take this transformation called the Legendre transform, and this basically is going to be the function whose derivative is inverse to the function that we're taking the Legendre transform of. And what is the meaning of this function? Well, this has a probabilistic interpretation. So this is a large deviation rate function from probability theory. And it describes the exponential decline of the probability of certain extreme events via a theorem called Cramer's theorem. And it's some strictly convex function that depends on the parameters of the carpet. So now that we've defined this rate function, if we fix a real number s, we can define the function t sub s to be a function that goes from the reals to the reals in this way. So it's going to be defined as s minus log m over log m times log n plus gamma, which is just log n over log m, times the rate function evaluated at t. Okay, so we define this function depending on a parameter s in terms of the rate function. Now we're going to define a sequence of numbers depending on some parameter s. So lowercase t sub 1 of s is going to be this quantity s minus log m over log m times log n. Then t sub 2 of s is going to be the image of that quantity under this function capital T sub s. And then t sub 3 of s is going to be the image under t sub s composed with itself again, etc., etc. So we start with this number and we keep iterating this function capital T sub s to form this sequence of numbers depending on a parameter s. Okay, and now we've done this setup, I think we're now ready to state the main result, which is as follows. So let's let lambda be any Bedford-McMullen carpet with non-uniform vertical fibers. Then for a fixed number theta between 0 and 1, we're going to define this quantity capital N depending on theta, which is going to be the natural number for which gamma to the power of minus capital L is less than theta, which is less than or equal to gamma to the minus L minus 1. So this tells us which block we're in between the different phase transitions that we saw in the graph previously. And the intermediate dimensions are going to be described separately on each of these different blocks. So for theta that lies within this range, the intermediate dimensions are going to be given by the solution S of theta between the Hausdorff and box dimensions to this equation here, right? This long equation. So what's going on here? So this is an equation in terms of two variables, theta and S, equaling 0. So theta appears in various places, and then S appears inside this function T sub L of S, which, if we recall, is defined in terms of iterating this function in terms of the rate function, capital L number of times. Okay, so we've got that quantity here, and then we've got its image under the rate function appearing here as well. So maybe this is quite a lot to take in, so let me just briefly recap. We've got this rate function from probability theory defined in terms of a Legendre transform, and it depends on the parameters in the IFS. We then use that to define this iterating function capital T sub S, and we iterate that function starting at a particular value depending on S to define a sequence in terms of S. We then look at the different blocks of values of theta separately, and within each of those blocks, the intermediate dimensions are described as the 0 set of this equation in terms of two variables, theta and S, where S appears in terms of that quantity that we keep iterating. Okay, so does anyone have any questions about the statement of the main result? Okay, if not, then I'll make a couple of remarks about it. So in particular, this shows that the intermediate dimensions exist in the sense that the upper and lower versions of the intermediate dimensions are going to be equal. And this is completely unsurprising because Bedford-McMullen carpets are homogeneous in scale, right? So they're inhomogeneous in space, but they are homogeneous in scale. So we wouldn't expect them to differ, but this is the first time that it's actually been shown that these dimensions exist. And another remark is that if the carpet has just two column types, so if they're just each column has either one particular number of maps in it or one other number of maps in it, then the rate function can be calculated completely explicitly. And therefore, this equation that describes the intermediate dimensions could also be calculated completely explicitly. But even if we don't just have two column types, the Legendre transform can easily be computed numerically, and that means that we can describe this function numerically, and therefore we can also describe the solution set of this function numerically, and that's what allows us to draw the plots of the intermediate dimensions. So the proof is quite long and complicated, so I won't have time to outline the whole proof, but I'll make a few remarks about the proof of the upper bound. So it involves constructing an explicit cover in quite a complicated way, using an increasing number of scales as theta gets small. So the scales that are used are going to be delta. Delta is going to denote the largest permissible scale. Then we also got to use delta to the power of gamma, right, which is a slightly smaller scale, and then delta to the power of gamma squared, and et cetera, all the way until delta to the power of gamma to the power of L minus 1. Then we've also got to use the very smallest scale, delta to the power of 1 over theta. Then we've got to use delta to the power of 1 over gamma theta, which is slightly bigger. We've got to use those bigger and bigger scales until we get to delta to the power of 1 over gamma to the L minus 1 theta. So when we're calculating dimensions, all we care is how the cost scales as delta to the power of some particular exponent. Okay, so using a cover that we can construct using these scales, that will get us the optimal exponent, which is enough to get the intermediate dimensions. But if we wanted to get the true optimal cost of the cover, then we couldn't just use these scales, we'd have to use all the different scales between delta and delta to the power of 1 over theta. This is the general case, but there are a couple of special cases where the proof simplifies substantially. It's still non-trivial and it's still new, but when theta is greater than or equal to 1 over gamma, then we can see that we only have to use the largest and smallest scales in the cover to work out the intermediate dimensions. So that's a much simpler case. And also, when theta is a negative integer power of gamma, then these two sequences of scales, they kind of coincide and line up with each other. So in that case, we've just got to use the scales delta, delta to the power of gamma, etc., up to delta to the power of gamma to the power of k. And that in that case, the construction of the cover is quite a bit simpler as well.
Amlan, I have a quick question.
Yeah.
What do you mean by true optimal cover uses all scales? Wait, isn't the cover at a fixed delta always going to have a finite number of elements? So what do you mean by that?
Yeah, so I mean that if you want the cover that actually minimizes the S cost, so the sum of the diameters of the cover raised to the power of S, such that that thing is as small as possible up to multiplication by some constant which depends only on the carpet. And if you want that to hold uniformly for all small delta, then you can't just get away with using these finitely many scales. You've got to use not all the different scales, but you'll have to use an increasingly large number of scales as delta goes to 0. You've basically does that make sense?
At least you mean more than these scales. Okay. So these scales are enough, like up to like some sort of like sub-exponential error. But if you want like a constant error term, you need to use more.
Yeah. So you've got to use like the size of you can to get the true optimal cover, you could cover one particular approximate square, and then like the next approximate square will have size like 1 over m, and you would have to like use that scale as well, and then the next iterate. So you'd have to use like all the different iterates if you wanted to get the true scales. You can't just leave like any kind of exponential gap between it. Yeah, so maybe that's the better way of saying it. You can't leave any kind of exponential gap between the different scales. Yeah, you've got to use all the different scales pretty much. Yeah.
Okay, thanks.
Amlan, you've gone a bit quiet again.
Oh, sorry. Thanks. That's really weird. I don't know why it happens. Okay. And what is the strategy for the proof? Well, we basically we break the carpet into approximate squares, and then we decide which parts of each approximate square to cover at which scale, depending on basically how the different parts of the symbolic representation of each approximate square relate to each other. So that's the complexity, is by looking at how the different parts relate to each other within the symbolic representation. But unfortunately, I don't really have time to go into the details of that. And one more thing I'd like to say is why this number gamma keeps cropping up everywhere in the formula. It's very, very significant, this number gamma, and the reason is just that if you have a cylinder of length delta for some delta, then its height at the height of that cylinder is going to be roughly delta to the power of gamma, which means that an approximate square of size delta is going to be made from stacking these cylinders of height delta to the power of gamma on top of each other. So that's why this number gamma keeps cropping up. And these are the first. This is the first time we've actually been able to prove that we need to use more than 2 scales in order to achieve the intermediate dimensions. In previous work with Jonathan Fraser, I showed that if we're constructing a cover that achieves the intermediate dimensions for continued fraction sets or other infinitely generated self-conformal sets, then the cover that we constructed used lots of different scales, but we didn't actually prove that you you had to use that many. You had to use more than 2 scales, although I'm sure that's true. And a couple more tools that are going to be used, that are used in the proof for the intermediate dimensions. One is going to be a variant of a mass distribution principle that was proved for the intermediate dimensions by Falconer, Fraser, and Kempton. So the lower bound is going to use a variant of that, among other things. And throughout the proof, we also use the method of types, which you might remember Istvan gave a talk earlier this year about how he used that to calculate the box dimensions of certain higher dimensional self-affine sponges. Okay, so what does the shape of the graph look like? So if we vary the parameters of the graph, then that can lead to a variety of different shapes. So here we see some particular carpet. We've got the overall shape looking like this. But then if we vary the parameters, in particular just little m and little n, then this can cause the graph to go down more steeply near theta equals 1. Then if we vary them some more, we can get this shape as well. Here, the graph drops below this line, this straight line joining the Hausdorff and box dimensions, and then it's got this kind of snaky shape. It rises above that straight line before falling down to the Hausdorff dimension again as theta goes to 0. So what are some properties of the graph that we can prove? Well, if we differentiate this formula for the intermediate dimensions and use implicit differentiation, we can show that the intermediate dimensions are going to be strictly increasing in theta, and in particular, we get a lower bound on the slope of the function, the left or right derivative, that depends only on the carpet and not on theta. So if you're allowing yourself bigger intervals, then that really is going to help you to decrease the dimension. Moreover, at every negative integer power of gamma, there is a phase transition in that the derivative is going to have a discontinuity. It's going to be, the left derivative will be less than the right derivative. And intuitively, the reason why this happens is because there's going to be a discrete jump in the number of scales that we're using to construct the optimal cover at these powers of gamma. So, for example, if theta lies between gamma to the -2 and gamma to the -1, then we're using 4 different scales. Then if theta is equal to gamma to the -3, then for that instant, we're using 3 scales, because there's this kind of collapsing going on. But then as theta decreases below gamma to the -3, then we've got to use 6 scales to achieve the optimal cover. So that's intuitively why we get these phase transitions. If we do some more differentiation and use some properties of the rate function, we can prove that the graph is going to be strictly concave between any pair of phase transitions, and moreover, we'll get we'll get some kind of uniformity over the range of theta. Moreover, between phase transitions, the graph is going to be real analytic. So the reason this is true is because the rate function is an analytic function, as the Legendre transform of an analytic function. So this tells us that this function of 2 variables is going to be analytic along any line segment. And then by a result of Sitchak, this says that the function of 2 variables will be jointly analytic in theta and s. So we can then apply the analytic version of the implicit function theorem to say that the implicit function theorem, to say that the 0 set, which describes the intermediate dimensions, has also got to be analytic. And as I mentioned before, we can also get the behavior near theta equals 0. And the way we do that is to estimate this quantity L of theta, which is just the number of these terms T sub I of S that we're iterating. We can estimate this in terms of the intermediate dimension, using the fact that the intermediate dimensions will be close to the Hausdorff dimension. and this function t sub the Hausdorff dimension has a neutral fixed point somewhere. So most of these t sub I quantities will cluster around that neutral fixed point. We can estimate how many of those there will be using Taylor's theorem. Okay, so just to summarize, yeah, we've got strictly increasing, we know it's asymptotic behavior near zero. We've got these countably many phase transitions, right, which we haven't seen in previous examples. And between those phase transitions, it's analytic and it's strictly concave. Okay, now what I'd now like to talk about is a rather unexpected connection to multifractal analysis. So nu is now going to denote the uniform Bernoulli measure supported on a Bedford-McMullen carpet. So that's the unique measure which satisfies this invariance identity for all Borel sets. And basically, we're giving mass 1 over n to each of the first level cylinders. And then within each of those cylinders, we divide the mass equally to each of the second level cylinders, et cetera, and this process is going to converge to give us the uniform Bernoulli measure supported on the carpet itself. So this is some fractal measure. So Kenyon and Perez in 1996 showed that this measure is exact dimensional, which means that the local dimension of this measure exists and is constant almost everywhere. So the local dimension just describes how the mass of a small ball scales with respect to r as r tends to 0. So this exists almost everywhere, but the complement of this set will have Lebesgue measure, will have measure 0. But when we have an interesting set with measure 0, the natural thing to do is usually to consider the Hausdorff dimension, and this motivates the definition of the multifractal spectrum. So when I talk about the multifractal spectrum, I'll mean the fine or Hausdorff multifractal spectrum. So the multifractal spectrum evaluates that a parameter alpha is going to be the Hausdorff dimension of the set of points x in the support, for which the local dimension equals alpha at that point. And this can be quite difficult to calculate in general, but for Bedford-McMullen carpets, they're actually one of the more complicated examples for which it has been computed explicitly. This was computed by Jordan and Ramps in 2011, building on previous work of King and Barral and Menzi. And the higher dimensional case has been studied by Lars Olsen. And we can use, we can look at, if you look at the formula of Jordan and Ramps carefully, it's also defined in terms of a certain Legendre transform. And if you do some manipulation of Legendre transforms, we have this interesting fact that the multifractal spectrum is directly related to this function I of t, which is exactly the same rate function that appears in the definition of the intermediate dimensions. Okay, so we've got this very direct relationship between the rate function and the multifractal spectrum of the uniform Bernoulli measure. And this hints at our next result, which says that if lambda and lambda primed are two Bedford-McMullen carpets with non-uniform fibers, then the intermediate dimensions are equal for the whole spectrum of theta, if and only if the corresponding uniform Bernoulli measures have the same multifractal spectra. Okay, so equality of intermediate dimensions is equivalent to equality of multifractal spectrum of the corresponding uniform Bernoulli measures, which is not something we were expecting when we first started this work. And in fact, we can say something more. So if we do have this equality of the intermediate dimensions, then in fact, both carpets can be defined on the same grid. And if the two carpets are defined on an m by n grid and an m primed by n primed grid respectively, then log n over log n primed has got to be equal to log m over log m primed, and moreover this quantity has got to be rational. So you've got this quite a strong condition for what it means for the intermediate dimensions to be equal. Now, if we assume that the two carpets are defined on the same m by n grid to begin with, then the equality of the multifractal spectra of the uniform measures was shown by Rao, Yang, and Zhang in 2020 to be equivalent to a very explicit condition that's explicit and checkable, that depends only on the parameters of the carpet. And in particular, if the two carpets are on the same grid with the same number of non-empty columns, then this condition simply says that the column sequence of one carpet has got to be a permutation of the column sequence of the other carpet. And if the two carpets are defined on the same grid, then we also have this interesting result that says that if the intermediate dimensions are equal for all theta in some small open interval, subinterval of the interval from 1 over gamma up to 1, then this actually forces the intermediate dimensions to be equal for the whole spectrum of theta, right? So that you've got this kind of rigidity that if they're equal for some small subinterval, as long as it lies in this range, that forces them to be equal for the whole spectrum of theta, provided the two carpets are defined on the same grid. So here are a couple of examples that illustrate interesting behavior of the intermediate dimensions. This is taken from an example of Rao, Yang, and Zhang. If we take the two carpets defined in this way, then they're both defined on the same grid, and they have different column sequences, but the intermediate dimensions can be shown directly using our formula to be equal for the two different carpets. And this is only possible because the number of non-empty columns is different here. Okay. And another example is that we can construct two different carpets on two different grids, which have the same intermediate dimensions on some interval from theta 0 to 1, but not for the whole spectrum of theta. And that's only possible if the two carpets are defined on two different grids, by the remark that I mentioned last slide. Okay, so that's a kind of a cool fact that we've got this equivalence between the multifractal spectrum and the intermediate dimensions being equal. But what's an actual application of this? Well, we can apply this to the problem of determining when two Bedford-McMullen carpets are bi-Lipschitz equivalent. Okay, so this is a very difficult problem in general. I don't think it's even known in this full generality for the case of self-similar Sierpinski carpets, which are defined on a square grid, right, with lowercase m equals lowercase n. But there's been partial progress towards this this problem by these authors listed here for Bedford-McMullen carpets. And the relevance of the intermediate dimensions here is that they can very easily be seen to be a bi-Lipschitz invariant. Okay. So as an immediate corollary of our previous theorem, we have the following result, which says that if we've got two Bedford-McMullen carpets with non-uniform vertical fibers, and we assume that they are bi-Lipschitz equivalent, then first of all, their uniform Bernoulli measures have got to have the same multifractal spectra. And also, it must be possible to define both the carpets on the same m by n grid. Okay. And if m1 by n1 and m2 by n2 are two grids on which the carpets can be defined, then we again have this relationship that log m1 over log m2 equals log n1 over log n2, and this has got to be rational. Okay, this equality here was proved by Fraser and Yu using the Asford spectrum, first of all. This result improves the result of Rao, Yang, and Zhang, where they assumed that both carpets were defined on the same grid, and they also assumed this rather unnatural topological assumption that says that the two carpets were totally disconnected, and they then showed that bi-Lipschitz equivalence implies that the uniform Bernoulli measures have got to have the same multifractal spectra. So we can remove these two assumptions using the intermediate dimensions. In particular, since a carpet is clearly bi-Lipschitz equivalent to itself, this says that if the same carpet is defined on an m by n grid and an m primed by n primed grid, then log m over log m primed equals log n over log n primed, and this has got to be rational. So this first equality was first proved, I think, by Fraser and Yu using the Asford spectrum. Both of these are kind of intuitively quite clear, but this rationality is basically saying that you can't have the same carpet defined on a 2 by 4 grid and also on a 3 by 9 grid or a 3 by anything else grid. It's kind of intuitive, but this would at least be one way to prove this. And here's an interesting example. We've constructed two carpets, lambda1 and lambda2, with these parameters. So m and n are rather big here, but we've constructed these in such a way that the intermediate dimensions are different because they've got different column sequences and the same number of non-empty columns, and they're defined on the same grid. But we've constructed these examples such that all the other usual dimensions are going to be equal. And I don't just mean the Hausdorff and box dimensions. We've constructed it in such a way that the Aswad dimensions will be equal, the lower dimensions, the Aswad spectrum, the lower spectrum, all of those will also be equal. If you arrange the rectangles, the choice of maps in the correct way, then you can guarantee that the carpets are not going to be totally disconnected. So the resultant bi-Lipschitz equivalence by Rao, Yang, and Zhang would not apply. But nonetheless, we can tell from our previous corollary using the intermediate dimensions that these two carpets cannot be bi-Lipschitz equivalent. And actually, you can do slightly better than just saying that the carpets are not bi-Lipschitz equivalent. You can also look at the Hölder distortion between the two carpets. So if F is some map from lambda primed into the plane R2 that is alpha Hölder, then it's straightforward to see that the intermediate dimensions of the image, f of lambda primed, is going to be less than or equal to 1 over alpha times the intermediate dimension of the original set. Okay, so here lambda prime could be any set. This is just a general Hölder distortion estimate for the intermediate dimensions, but for our application, we're going to take lambda primed to be this one of these Bedford-McMullen carpets here. I think it's going to be that the second one, lambda primed, is going to be lambda 2. So if we now assume that we've got this map from lambda primed onto R2, and we assume that the image of lambda primed contains the other Bedford-McMullen carpet, lambda, then what we can do is we can look at the ratio of the intermediate dimensions of the two carpets, and that's going to look something like this. And you can see that the smallest value that this can take will be attained when theta equals gamma to the -2, which in this case is approximately equal to 0.40. And then if we just rearrange this inequality that gives the Hölder distortion estimate, then we get that alpha has got to be less than or equal to the intermediate dimension at the intermediate dimension of lambda primed divided by the intermediate dimension of lambda at this particular value of theta that we've chosen. And then we can see on this graph and compute numerically that this quantity has got to be less than 0.9995. So this can be considered to be like a quantitative improvement of the assertion that these two carpets are not bi-Lipschitz equivalent, right? We get this very explicit bound for the Hölder distortion between them. With John Fraser, I used a similar kind of argument to show that the intermediate dimensions can sometimes be used to give better Hölder distortion estimates for maps between continued fraction sets as well. And that can be that can give a better estimate than either the Hausdorff or the box dimensions. Okay, and just to wrap up, I'll just mention a couple of what seem to be open problems. So one natural problem along these lines would be to see if further progress can be made towards characterizing when two Bedford-McMullen carpets are bi-Lipschitz equivalent. A full characterization would be very difficult, but perhaps this simpler question might be more tractable. Do there exist two Bedford-McMullen carpets with non-uniform fibers defined on the same grid, which have different column sequences and which are bi-Lipschitz equivalent? So if this is impossible, then I think that dimension theory cannot be used to prove that this is impossible, because remember we had that example where the column sequences were different, but the intermediate dimensions were the same. I think if this is impossible, then it would require a different kind of techniques to prove this. If there is such a map, then maybe there's a simple example showing that. And okay, often people ask about generalizations or higher dimensions. So another thing that could be asked, I suppose, is what can be said about the intermediate dimensions of other classes of self-affine sets with different Hausdorff and box dimensions. So for example, higher dimensional Bedford-McMullen sponges or Lale-Getzuras carpets or sponges, or Baranski carpets or sponges. And my feeling is that to try and tackle this problem, you'd probably have to use some of the similar kind of ideas that we've used in our work, but that there would be very substantial additional complications. So in particular, in the higher dimensional case, you've got to look at approximate cubes or approximate hypercubes instead of approximate squares. And that would not just be described by one part of a string and then another part of a string. There would be more different parts of the string that you'd have to look at. And I think that would introduce a lot of complications. And then for the other classes like Lale-Getzuras or Baranski carpets, the issue is that we don't have such a clear quantity like gamma, right? Like log n over log n. There's not such a clear quantity for those carpets. So I think that would cause a lot of complications as well. So I'll stop there. Thank you for listening.
Okay, thank you very much, Amlan. Do we have any questions? Please feel free to put them in the chat or unmute yourself and ask directly.
Yeah, I have a, oh, Kenneth, go ahead, sorry. Oh, okay.
You go first, Alex.
Okay. Yeah, I have 3 questions I've written down. Okay. So you mentioned this one rigidity result, that if you have like an open set between 1 over gamma and 1, right? That if it's equal on some open set, then it's going to go over. So for example, like maybe like other rigidity results, like let's say it's equal at all points of the form 1 over gamma to the n. Is this enough to force them to be equal?
Yeah, good question. I don't know. We haven't really thought about that. But you could ask other questions about the form. But yeah, we don't know that. Yeah.
Sure. Okay. So you also mentioned that you have an example where the intermediate dimensions are different, but all the other dimensions are the same.
Yeah.
Can the opposite happen? Can you have 2 things with equal intermediate dimensions, but like a SWAD spectrum or something else is different? Or does equal intermediate dimensions imply all the other ones?
I think it implies that all the others are equal, because by our second result, if the intermediate dimensions are equal, then this says that the multifractal spectrum has got to be equal. And then I think that will tell you that the other ones will be equal. Yeah, I'm not 100% sure, but I think that will tell you that the other common notions should be equal, because the Aswad spectrum is really and the Aswad dimension is really just dependent on the column with the largest number of maps. That plays a key role, and the lower dimension, the lower spectrum, is about the column with the smallest number of maps, whereas the intermediate dimensions kind of take into account all the different columns using through the rate function. So I think that that's not possible. Yeah.
Okay, makes sense. All right, and then just one last, not really a question. So
Sure.
In general, if you have 2 sets with intermediate dimensions that are different, you're always going to get a quantitative estimate on Holder exponent, right?
Yeah.
That's just generally true, right?
Yeah.
Okay. So there's nothing specialized. All right, that's it for me.
So yeah, if you've got 2 sets with different intermediate dimensions, I suppose the point is to find examples where, okay, in the case of Bedford-McMullen carpets, people do care about them. Generally, they care about being bi-Lipschitz, but also the intermediate dimensions will give better information than the Hausdorff and box dimensions. I suppose that's really the point that I was trying to illustrate with that example. Yeah.
Makes sense. Cool.
Thanks for the questions. Yeah, thanks.
Thank you, Alex. Kenneth?
Yeah, just a couple of things. Firstly, how did you come up with this formula? Which did you approach it from above or below first? And secondly, it just struck me, is there some sort of renormalization going on that maps you from one concave section to the next in some way?
Okay, so how did we come up with this? Well, through quite a tenuous route. We thought that.
Sorry, Amlan, you've gone quiet just at that moment.
Okay. Okay. So how did we come up with this? Well, first of all, we realized that we could get the result for theta greater than 1 over gamma. We then thought that we could use this to extend this to smaller values of theta using just the scales delta, delta power of gamma squared, etc., and the very smallest scale. And that gave us an upper bound. But then we realized that the lower bound that we got didn't quite match, and that to get a matching lower bound, we also have to add in the scales delta to the power of 1 over theta, delta to the power of 1 over gamma theta, etc. So we've got to use all of those scales as well. And then after that, we came up with the construction of the rather intricate cover that covers all the different parts of the carpet using those scales. Mm-hmm. So it was kind of, it's kind of different to how results have been able to be come up with for other sets, right? Because the lower bound is in some sense more natural to suggest this formula. And can you get some kind of a renormalization? Not really. I don't think there's any kind of direct relationship between.
There isn't a natural mapping which takes one section onto the next.
No, not that I'm aware of. No, because it's defined by in terms of iteration of that function in terms of the rate function a different number of times, and then it's defined as the zero set. So I can't see any obvious way of mapping from one section to the other. No.
Okay, thank you.
Thanks.
Yeah, thanks very much, Kenneth. Other questions? I have a couple of sort of vague questions.
Sure.
So looking just looking at these pictures that you've got, it sort of starts to look smoother as you go towards zero, just because I guess the intervals are getting very close together, and maybe I don't know whether the phase transitions are actually getting less severe, but it sort of looks that way. Is there any way of like quantifying that statement, or?
Yeah. So the ratio of the left derivative to the right derivative at the phase transition, that tends to a particular number between a particular positive finite number as we go down to the different phase transitions. So I suppose it just looks less dramatic because the whole derivative is very large, but the actual ratio of the left derivative to the right derivative is tending to some fixed number. Yeah.
Yeah, to make that not be the case, you'd have to make it grow somehow.
Yes.
Yeah. Okay. And another sort of vague question. So if you were, I mean, I think this is a really interesting point you made about the, going to Laliget-Zuris or even higher dimensional sponges. There isn't such an obvious candidate for this important number gamma. Do you think there's any chance that for certain Laliget-Zuris carpets you might get no phase transitions because everything sort of averages out?
I really don't know. It's possible. If that did happen, I feel like it would be difficult to work out and prove exactly what the intermediate dimensions would be. Yeah, I don't know, but I feel like if one was going to try to work out, like try to study the intermediate dimensions of such sets, a more realistic thing to try to do rather than working them out exactly in general would be to maybe look at behavior near theta equals 0, where you might be able to say something much more concrete and quantitative, and maybe look at applications of that. Yeah.
Okay, thanks.
Thanks.
Any other questions? Okay, in that case, let me represent the group and thank you on everyone's behalf for a great talk, Amlan, and thanks everyone for coming. And do remember that we have a talk next week, which was not initially scheduled. So Han Yu will be giving the analysis seminar at the usual slot next week. Okay, thanks very much, everyone. Bye.
Thanks. Bye.